Welcome, class. Grab a seat, and let's jump straight into today's explainer. Today, we're tackling a deceptively simple problem in computer science, finding the maximum and minimum numbers in an array. It sounds totally basic, right? Like something you'd probably code up in your very first week. But as we start pulling back the layers today, you're going to see how this super fundamental task actually opens up a massive, fascinating debate about pure mathematical theory versus the actual metal of our machines. Here's our syllabus for today. We'll start with Algorithm 101. Check out the naive brute force approach, look at the tournament of elements, move into the pairing optimization, and wrap up with theory versus real-world performance. All right, Section 1. Welcome to Algorithm 101, defining the problem. So, I want to pose this fundamental question to you, the class. What does it actually cost us, computationally speaking, to find these two extreme values? Think about it. If you have an array of, let's say, 1,000,000 random numbers, you need to hunt down the absolute largest number and the absolute smallest number. In computer science, we measure the cost of this whole operation by counting the number of comparisons. Basically, every single time the computer has to ask the question, hey, is x greater than y?
Moving to Section 2, the naive brute force approach, our baseline. Let's start with the most basic brute force iterative method. Honestly, this is exactly what you would likely code on your first day on the job as a software engineer. We simply loop through the array. First, you just grab the very first element and declare it to be both your current minimum and your current maximum. Boom, done. Then you step through every single remaining number in that array one by one. And for every single new number, you ask two questions. First, is this new number greater than my current maximum? If yes, update it. Second, is this new number less than my current minimum? If yes, update the minimum. It's super intuitive, and hey, it definitely gets the job done.
But mathematically speaking, what's the actual cost of this naive method? Well, finding the minimum independently takes n-1 comparisons, and finding the maximum independently takes another n-1 comparisons. Because we're asking two distinct questions for pretty much every element in a set of n elements, we end up with a total upper bound of 2n-2 comparisons.
But I have to ask you, is this the absolute best we can do for algorithmic efficiency? Are we just completely wasting computational power doing it this way? To really figure that out, we have to look at the mathematical floor of the problem.
Which brings us to Section 3, the tournament of elements, visualizing comparisons. To really understand our mathematical floor here, let's look at the problem through the lens of a sports tournament. This is actually a famous analogy from Thomas Corman's classic algorithm textbook. Think of every single mathematical comparison as a head-to-head match in a tournament. If we just want to find the minimum value in an array, every single element has to step into the ring. And in a minimum tournament, the smaller of the two elements wins the match and advances to the next round.
So the crucial observation here, it's that n-1 comparisons are absolutely necessary just to find one of these extremes. I mean, think about it. To definitively crown one overall winner, the absolute minimum, every single other element mathematically has to be proven a loser at least once. Therefore, n-1 comparisons is the absolute minimum cost just to find the smallest number, and naturally it takes another n-1 to find the largest.
All right, Section 4, the pairing optimization. Working smarter.
Now, what's really interesting here is how we can actually combine the search for both the min and the max simultaneously. This lets us beat that 2n-2 baseline we established earlier. Instead of processing elements one by one and making two comparisons for each against the running min and max, we're going to process the incoming elements in pairs. Let's say we pull the next two numbers from our array. Step 1, we compare them against each other. Boom. Now we know exactly which one is the local winner and which one is the local loser. Step 2, we take the smaller of the two and compare it only to the current running minimum. And Step 3, we take the larger of the two and compare it only to our current running maximum.
By doing this for an even set of numbers, we drop our total comparisons dramatically. Instead of making 4 comparisons for every 2 elements, like we did back in the naive method, we are now only making 3 comparisons for every 2 elements. We compare the pair, then check the low against the min and the high against the max. This brings our mathematical worst-case complexity down to exactly 3n divided by 2 minus 2.
And this just brilliantly illustrates how the divide-and-conquer pairing method is asymptotically optimal. Mathematically, it is vastly superior. In a massive data set, literally eliminating 25% of your total comparisons just by processing elements in pairs, that is a huge theoretical win. In the realm of pure algorithm analysis, the pairing method is the undisputed champion. It's a beautifully elegant, optimized solution.
But wait, Section 5, theory versus real-world performance, the complication.
Let's see how all of this builds into a fascinating complication, straight from a real-world Stack Overflow debate. Because, class, as you know, computer science isn't just about math on a whiteboard. It's about executing code on a physical silicon chip. A developer on Stack Overflow named Rocky Scott decided to actually test these two concepts against each other in VBA. He pitted the naive basic 2n-2 loop against the mathematically superior divide-and-conquer pairing method. And he made a completely shocking discovery. The theoretically worse brute force method actually ran way faster.
Looking at the benchmark data spanning 10 million function calls, the recursive optimization was completely crushed by this simple loop. For a small array of just 10 items, the brute force method was 2.9 times faster. But incredibly, for a massive array of 1 million items, the brute force method was 3.4 times faster. Let that sink in. The algorithm that was mathematically supposed to save 25% of the computer's time was actually taking over 3 times as long to execute.
So why did this happen? Well, because pure theoretical math ignores real machine hardware. The developer community really dug into this and found a few main culprits. First up, recursion overhead. Many elegant divide-and-conquer algorithms use recursive function calls, which means the computer has to constantly open and close new memory stack frames. That is incredibly slow compared to a flat, simple loop. Second, modern CPUs use something called branch prediction. Basically, a CPU tries to guess the outcome of a comparison before it even happens to speed things up. In a simple brute force loop iterating through a million random numbers, the chances of finding a new maximum get smaller and smaller with every single step. The CPU actually learns this pattern, predicts that the if statement will be false, and just blazes through the loop with incredible efficiency. Complex paired comparisons completely disrupt this hardware-level rhythm. Add in the cost of memory allocation and reassignments, and the math just doesn't translate to the metal.
Class dismissed with this final homework thought. Algorithmic theory is absolutely crucial for understanding the limits of computation, right? You have to know the math. But a good computer scientist knows that you must always test your beautiful theories against the unforgiving metal of real-world hardware. Because sometimes the absolute dumbest, most naive loop is exactly what the microchip actually wants. Thanks for joining today's explainer, and I'll see you in the next one.